first I want to thank to Vijay to invite me here. I will represent the field end customer and happy customer of Vijay Technology. I represent the utility company. We provide electrical, gas, and steam service to New York area. My department mostly deal with high voltage underground cables. Just briefly about the department, we have 334 underground feeders, and we're talking about voltage level between 69,000 volts to 345,000 volts. So this is at a cable supply regions, not just the houses. We have about 750 circuit miles. Most feeders are at a pipe type feeders. Average age of the feeders, 47 years old. Oldest feeders around 60, 65 years old. And they keep serving. And this is very important for us to assess the condition of these feeders, because as you well know, to completely upgrade infrastructure is very costly and will be very long process. So that's why for us it's very important to assess the condition of the feeders. This is a slide especially for you to just explain what are the feeders. It's not just a cable and a pipe. It's a pretty complex system. We have a steel pipe, 1/4 inch thick. Inside we have 3 conductor cable, mostly at a paper insulated, with laminated shield here, and they all under the high pressure dielectric fluid. The pressure can go up to 250 psi in this system. This is a typical picture of, you can stand there. This is a typical picture of our manholes or walls, underground walls. You can see there pipes, and of course when we splice, it's much thicker pipe. It can go up to 24 inches in the diameter here. So it looks the big wall, but it's very tough and at a tight space inside here. So for our future, the discussion, steel thickness, 1/4 inch, overlap at a casing 6 inches there, it's overlap. So if we need to penetrate with X-ray, it's going to be almost 1 inch of the penetration of the steel. We use X-ray for over 50, 60 years, of course. We use radioactive source, cobalt-60 or iridium. Mostly we use to check welds when we weld the pipes. However, lately, when feeder became 40, 50, 60 years old, something started happening and we cannot take them out of service. We start using it more and more. And by using conventional radioactive sources, has a few negative sides. So first of all, it's very small and light equipment. As you saw here on the picture, we can bring it to the field. This is a plus, of course. Easy 24/7 availability, and it's not expensive at all. However, it takes time to process the film. It's also very low quality, and most important, we experienced it a few times, then that lead box will not close. So then it's actually a radioactive hazard. You need to evacuate the area. So it's not a problem until it's happened only once. Once it happened, you start thinking twice before you use it. So when we start use the digital X-ray technology, it happened, if I remember correctly, in 2011. So we have 2 major criteria. One, we have very high rate of the penetration, high power to penetrate 1-inch steel. Second criteria, we need to fit it inside our manholes. So many people can provide, as you've seen, big accelerator, big equipment, but none of them can be fitted in our manhole. Number 3 is mobility, so we can bring it to the site and make it right there at the site. So we start with Vijay, T, so that's equipment what we use at a power source, at the Betatron itself, and control box. These 3 pieces we can fit into the manhole, and we start use them from 2011. Of course, important part for us is the safety of our workers and safety of the people who walk around. New Yorkers are very curious people. Every time we do something like that, everybody come, picture with a cell phone, wants to go in. Especially when they see radioactive hazard, it's even more attraction for people to come there. So that's why safety is very important. You see the regular setup, mostly we've done everything in the night, of course, so to minimize exposure to the general public, of course. What has worked for us well, it's underground walls. It's actually 1 foot thick concrete inside, so when we shoot from up to down, it's actually safe for people. If it's not, so we can use lead protective plate just to cover hatches, and of course we evacuate area here. We have warning light, we have all retractive devices, and that's our first, the picture was made, I believe, in 2012 when we just start using equipment. So this is our area. We normally set up 15 feet radius around that equipment. We use lead paint. We constantly monitor radiation level while we're shooting. Now is interesting part, is examples, real examples. So as I said, it's a 40, 50, 60 years old system, and it's moved inside at the dielectric fluid, back and forth, many times. So mechanical problems start happening sometimes, so if we detect them, that will work very good for New York City, for people of New York City. Just to take out that system for inspection will probably cost a few $100,000. If system fail and you need to repair it, it's going over $1 million. It's not just what you see there. You need to freeze the electric fluid. You need to take system out of service. It's dozens of people work on it nonstop 24/7, because in New York City, like everywhere else probably too, no one accepts interruption in electrical supply. So just a few examples here. First example, we find out the splice moved in the manhole back and forth, and that's what we did first inspection. That's what we found. You see the grounding rope was ripped off from here. It's supposed to be like that, tied here. This is how it's supposed to be. This is a picture how it's supposed to be. And this is what we found. So you see what we saw on the X-ray image, and here you see when we open the casing. I made a picture so you see the actual, how it looks. So first, as any company, we're very conservative, we're very suspicious before we use anything. We want to validate the technology. We want to understand whatever we see, it's exactly what it is. So this is, you can see there, great example here. So first, it's obvious, you can see physical disruption. However, for us, it was most important to understand insulation level. What happened with insulation, with all electrical components? So you can see here on the first picture what we saw. It dragged my attention. I saw something like that, and all these tapes unravel, which was very hard to understand what is that. At that time, I remember we came to VJT, and we did some lab testing, and after we did that, it took me probably a few weeks to convince my management to take that feeder off. As I told you, just take it off, it's a few $100,000. We took it off, we opened it, and that's what we found. This is exactly the picture, and this is an X-ray image there. You see a burning already started there. So we prevent fall. We prevent fall on 345,000 volt system, which may cost more than $1 million repair. We did it, and that was the first big successful case back in 2000, I believe, 14, right? That's what happened. So then we start to use more. We create program. Now we X-ray suspected joints, and we monitor program. And we found something else. And inside we have a lot of supporting parts. So you can see there shielding, for example, there, and you see that pinch here and pinch there. So cleanness of the image, it's very important for us, and also we work with VGT to understand the density of the materials to separate between paper, metal, copper mesh, and that helps us to assess condition of the joint. This particular case, in addition to the quarter-inch casing and overlapping, we have a device called diffusion chamber. I don't want to explain it deeper what is that, but it's another tube inside. So basically here, you can see it's approximately 1.25 inches thickness of the metal for penetration. Now, regular conventional source, radioactive source, when we did that, we cannot see anything. It's completely black. That's another case. We have a device called full stop joint. So that joint has epoxy bushing inside. And what happened here, that bushing cracked. But amount of steel bolts around, not allowed to X-ray to see clear picture. It took us a few hours to find the right angle, and I was listening to your presentation in the morning, right, about the right angle, when that's exactly the case. When you take the right angle, we will see the crack of the epoxy bushing, and that's the crack what we see here, right there. But we're supposed to find the right angle. When we did that, it was easy to make a decision and replace it. But again, everything happened proactively, and this is very important to state. This is just a typical picture of connection. So we start work more and more. So first we look for any mechanical disruption. Second, we look for detail of insulation, mesh. Now we assessing connectors. You know, when cable connect together and shoot together, it's always the gap between, right? You see that gap here. You cannot avoid that gap. However, then its gap became bigger, meaning after many years in service and some fault condition on the feeder somewhere here, that connection may fail, and cable start moving apart. If you can detect that, that's our next step, and that's what and that you can see there, connector, the space right there. This is a real picture from recent development. You see here how big the space there, meaning this is the next step for replacement, next candidate for replacement. You also can see there gaps here on the edge of connector, which you have a tape, so tape move. What it tells to us, everything moved this direction. So again, it's another case, like third or fourth case, what I show you. We learning and we developing process proactively address issues, keep system which is 50, 60 years old in service for next probably 100 years. Replace it, it's super costly. It's billions of dollars. So we start with R&D project, and after R&D project, we did field evaluation. And after we finished that process somewhere in 2013, we developed routine X-ray inspection with the pipe type joints. I want to give the benefits to Vijay. From the beginning, to inspect fully joint, starting with mobilization to finish, took us 48 hours. Now it's take 8 hours. So that's improvement, huge improvement. They have unit which come when we call 24 hours at a 7-day a week. They can come, they can go into the manhole. They work by themselves. They only need 2 people who come, open the hatch, and put the cones around. So that's, I can give benefits to Vijay. They really help us to make that process much easier. We also find out that in the manhole we have joints very close to the wall, so we cannot go circumferential around and find any angle. So we start work with VGT to develop limited angle CT technology for our manholes. I will have a few slides further I can show you. So this is just at a timeline of accomplishment up to date. As I said, in 2012, we proactively replace a joint before failure. In 2013, we X-ray 3 joints, and we also recommend them to replace. In 2014, we have some instance on one of the New York bridges. We use VGT, so we check. That's another example. We have few suppliers who supply us plastic mold for the joints. One of the joint, and they test them at the factory, they bring them to the field. And what happened here in this particular case, the joint was defected right after factory. They missed it through the tests. So what we developed right after that instances, we developed with VGT a process which allowed us to inspect the joint before it's come to the field. So we inspected more than 50 joints, and I don't want to say what, but we rejected a big amount of them. So, and actually we saved our system from unwanted failure. And in 2016 we start 3D testing, 3D system. So now also we have first goal to check if it's really works. So what we did, we cut the joint, which is 22 feet long, and give it to VGT lab in Connecticut. And they play with that, and they develop, and they show us in the first place, this is doable. They show us images which we like. Second step, we develop technique to get 360 joint image. And now we're in the third phase to have a full prototype, should be tested next few weeks. This is example, we cut that joint and we give it to VGT. This is a pipe with a cable with a splice inside. You see this is in their lab. That's what they're testing with the same equipment what we use right now for 2D X-ray. This is a prototype already inside the manhole. First prototype, of course, rotating inside the manhole. This is a picture from top, from the ground. This is phase 2. And we are now in, and this is results of the phase 2. You see there the pipe. You see this is a supporting, we call it spider, but it's actually support of the free conductor cable. You see here 3 cables, and you see this 3 small, this is the grounding cables here also. So that CT, of course, was done in the lab. You don't have that luxury in the field. But we're working right now, and this is results of the system which we'll be testing next few weeks. You can see results here. It's much better results. Of course, we have long way to work, but this is impressive achievement, what I can tell from the customer perspective. It helps us to assess our system, to maintain our system, and to provide the best service for New Yorkers.